So last class we learned about infinite series. We learned that when you have a sequence like this, n from 1 to infinity, or n from 0 to infinity, or any other natural number, based on this sequence, you can build something called a series. And what you do is you have to just add up all the terms from the first one up to the end, and then you have a series. And with some types of series, you can evaluate this sum. And the ones that, the way you evaluate this sum is that you create something called a sequence of partial sums. That is, based on this sequence, which we can call, for example, the original sequence. Based on this, you create another sequence called the sequence of partial sums. And the way you make that is like this. You say S1 is simply A1, S2 is A1 plus A2, all the way to Sn. That's A1 plus A2 all the way to San. That is, you just add up the terms from the first one to the nth one, uppercase N, and then you have a sequence, S1, S2, S3, S4. That's a sequence of, that's a list of numbers. And this sequence is an infinite sequence. Now, in order to evaluate S, you take the limit of Sn as n approaches infinity. Last class, we looked at two cases, two types of series where you can find the formula for Sn. So there is a way of finding a formula for Sn, and if you can find a formula for Sn, then you can take the limit of that as n approaches infinity and see whether your series approaches a finite number or not. So if this limit exists, and if this limit is equal a finite number, then you would say that the series is convergent. Otherwise, you would say that the series is divergent. And those two types of problems, those two types of series that we looked at, they were the telescoping series, like this one. So if you have something like this, you have sigma 1 over n times n plus 1, n from 1 to infinity, then if you write down Sn, you can see that all the terms cancel out except for the first few or the first last ones, and then you can find the limit of Sn. So the trick for this was, first of all, you use the techniques of partial fractions. You can write this as 1 over n minus 1 over n minus 1. And then when you want to write Sn, you have to, Sn is going to be sigma n from 1 to uppercase N of 1 over n minus 1 over n minus 1. And first n is 1, so you get 1 minus 1 over 2, plus then n is 2, you get 1 over 2 minus 1 over 3. Then it's going to be 3, so you get 1 over 3 minus 1 over 4. And this keeps on until the nth term, I mean uppercase N. So you get 1 over n minus 1 over n minus 1. Sorry, it's going to be plus and plus 1. And at that point, you can see that this term cancels this one cancels this one will be canceled, the one right after that, and the one right before this is going to cancel this one. And you will be left with only 1 minus 1 over n plus 1. That is, we found the formula for Sn. Now we can easily take the limit of that. That's 1. So now we can see that this series here is equal 1. So I gave you a couple examples like that. This type of series are called telescoping series, and the reason that's called telescoping, think of one of those old-fashioned telescopes that they just you can fold it, it collapses, yes, and you can open it. So if you look at this, it collapses because these terms that are close to each other, they cancel out, and the only thing that is left at the end is the first term and the last term. Sometimes it's the first two terms and the last two terms, and that's why this is called the telescoping series. So that was one type. The other type we looked at for which we can find Sn are geometric series. And geometric series, they are built on geometric sequences. That is, if you have a sequence like this, a r to the power of n, and from 0 to... Yes?
I just had a question before. There's one question in 7.3 that gives you Sn and and you have to find An, and I didn't really know how to do that.
Okay, I'm gonna get back to that later. Okay. Just remind me later on. So this is called the geometric sequence. And for example, imagine A is 3 and R, which is called, so A is called the initial term and R is called the common ratio. Let's say it's 1/2. So first you have 3 1/2 to the power of 0, then you have 3 times 1/2 to the power of 1, then you have 3 times 1/2 to the power of 2, and this sequence goes on like this. Such a sequence is called the geometric sequence, and if you build a series based on that sequence, then this series would be called a geometric series. Now, for a geometric series, we proved that Sn in terms in the case of a geometric series is going to be a times 1 minus r to the power of n plus 1 over 1 minus r. And the algebra is really simple. So we went over this last class. So this is another scenario where you can find Sn. I want to tell you this. For most series that you see, you cannot find Sn. You can only find Sn for these two types of series, the telescoping ones and the geometric ones. And then by studying this, we learned that the limit of Sn as n approaches infinity would be a over 1 minus r if and only if absolute value of r is less than 1. Because if absolute value of r is less than 1, then this part, r to the power of n plus 1, is going to approach 0. It will not happen if r is greater than 1 or equal 1 or equal -1 or less than -1. This will not happen. It will only happen if absolute value of r is less than 1. That is, r is between -1 and 1. In that case, this part will approach 0, and that's the only part which has uppercase n. So you get 1 times a, just a over 1 minus r. So we had this theorem here for geometric series. The moment you see that r, the common ratio, is between -1 and 1, the series converges to a over 1 minus r, and otherwise the series diverges. So for example, this, with these a and r that I have here, so if you have something like this, and from 0 to infinity of 3 times 1/2 to the power of n, then you ask yourself, okay, what is a? First of all, it's obvious that the common ratio 1/2 is between -1 and 1. So this series converges. Then you ask yourself, what is a? A is the first term. So you have to look at this index here. Where does the series begin? It begins at 0. So I'm going to plug in 0 into this and calculate a. When I plug in 0 into this, I get 3. And then what is r? R is obvious. It's 1/2. And then I just plug in the values into the formula, a over 1 minus r. So it's 3 over 1 minus 1 over 2. So it's going to be 6. Now, if I have the same series, but it begins at 1, how do I calculate? It is still geometric, but an r is still 1 over 2, but a would be different. Yes, because when you plug in the first, when you want to calculate the first term, you have to plug in 1. And 1 into this will give you 3 over 2. So in that case, s would be equal 3 over 2 over 1 minus 1 over 2. It would be 3. Make sense? So you just need to find, as long as you recognize that this is a geometric series, you just need to find a by plugging in the first number into the general term, and r is always obvious. So that was what we learned last class, and today we're going to continue our discussion about series, and we're going to look at series where you cannot necessarily find Sn. But even though you cannot find Sn, there are some other techniques that you can tell whether the series diverges or converges. And sometimes you can just tell whether it diverges or converges. You cannot tell what to. For example, you can see that the series converges, but you cannot calculate exactly what to. You can find an approximation for that by adding up sufficiently large number of the terms of the series, but you will not be able to say exactly what does it converge to. So 11.4, series with positive terms. We are not going to study series with negative terms in this course. So we are dealing with series where an, let's say n starts from 1 to infinity. These values, a1, a2, a3, all the way, the values of this sequence, all of them are positive. The first theorem that you have is theorem 3, which says if you have a series an, and from 1 to infinity, let's call that S. If this series converges, then the limit of an, and an is the values of this sequence that builds the series, would be exactly 0. So how can we use this? Because it doesn't tell us whether the series converges or diverges. It doesn't tell us that. Yes. What it tells us is that if you know that the series converges, then the limit of the sequence that the series is built upon, that limit is going to be 0. That means if you just think of this an, which is the general term of the sequence which built this series, that limit is going to be 0. The way we use this is by asking ourselves, what happens if this limit is not 0? Yes. So let me explain that first. Imagine I have P, then Q. Yes. So you have a statement P and you have another statement Q. So you say that if P, then Q. Then this is equal, or this is equivalent to no Q, then no P. Because if there would be P, there would be Q. So no Q means no P. So we are using this theorem like that. We know that if the series converges, then the limit of the general term is equal 0. That means if the limit of the general term is not 0, then automatically the series is not convergent, it's divergent. So this theorem, by this rule here, leads to another theorem, which says if the limit of an approaches infinity, if that limit is not 0, then you can be 100% sure that the series sigma an and from 1 to infinity diverges. So this is called the test for divergence. It's a test that will tell you whether a series diverges or not. But if this limit here, if that's equals 0, then you have no conclusion. So for example, if limit of n approaches 0 is equal 0, then what do you conclude? No conclusion. That's why this is called the test for divergence, because it will tell you whether the series is divergent or not, but it cannot tell you whether it's convergent. This test is not a sufficient test to tell you whether the series is convergent. However, it can tell you whether it's divergent if you have this. So let me give you some examples. Okay, yeah, this is the theorem. If the limit does not exist, or if the limit is not equal 0, so it could also not exist, then you know that the series diverges. So I have to add it here. If this limit is not equal 0, or if this limit an does not exist, in both cases, you know that the series is divergent. So let's take a look at these two examples here. Limit of -1 to the power of n minus 1 and from 1 to infinity. No, not limit. Sigma -1 to the power of n minus 1 and from 1 to infinity. The first thing that you do should always be test for divergence. If you want to know whether a series is divergent or convergent, the first thing that you always do would be the test for divergence. And the reason for that is this is the simplest test. And if this test works, then you don't have to do anything else. If the test does not work, then you have to resort to other tests, because this test could be inconclusive. Yes. So how do you test that? You just take the limit of the general term. Now, if this limit is 0, the test is inconclusive. That means the test would be useless if this limit is 0. Yes. However, if this limit is not 0, or if this limit does not exist, then you know that the series is divergent. Yes. And in this case, you can see that this limit does not exist, because this sequence, if it starts from 1, it's going to be -1 to power of -1. So it's -1, then 1, then -1, then 1, then -1, then 1. So this sequence does not approach any number. It just fluctuates between -1 and 1. So since this limit does not exist, then I can be sure that this series over here is divergent by this theorem, because it says that if the limit does not exist, or if the limit is not equal 0, then you can be sure that the series is divergent. Now let's take a look at the next one. Any questions about the first one? Then we have 2n squared plus 1 over 3n squared minus 1, and from 1 to infinity. And the test for divergence is always the first thing that we do. We're going to take the limit of the general term as n approaches infinity. And this is like having the limit of 3x squared plus 1 over 3x squared minus 1. You can use the dominant term technique. That is, you just keep this term and this term, because these are the dominant terms. So you get limit of 2n squared over 3n squared as n approaches infinity, and that's going to be 2 over 3. And you can see that 2 over 3 is not equal 0. So by the test for divergence, we know that if this limit does not exist, or if it is not 0, then the series would be divergent. So this series is also divergent. So again, I want to emphasize that this test is only useful if the limit is not 0 or if the limit does not exist. If the limit is equal 0, then you know nothing about that series. And I hope there is there is no example of like that, but I'm going to show you examples. So imagine you have something like this. You have 1 over n from 1 to infinity. So you're dealing with this series. Sigma 1 over n from 1 to infinity. So this series is actually 1 plus 1 over 2 plus 1 over 3 all the way. Yes. So if you take the limit of 1 over n as n approaches infinity, you can see that this limit is equal to 0. Yes. So this test does not tell you anything about this series. This series could be convergent, it could be divergent. You're going to use another test for that, which is called the integral test, which we'll talk about after. But I want to emphasize that the test for divergence, when you take the limit and this limit is equal to 0, that would be inconclusive. Inconclusive. Same for this one. Let's say sigma 1 over n squared, n from 1 to infinity. That is 1 over 1 plus 1 over 2 to the power of 4, then 1 over 9, then 1 over 16. So this series. Again, if you take the limit of 1 over n squared as n approaches infinity, that's going to be 0. So that means the test for divergence would be inconclusive. It doesn't tell you anything about whether this series is convergent or divergent. And using the integral test, I'm going to show you that this one here is actually divergent, and this one here is convergent. So is everything clear about the test for divergence? This should be the first test that you always use, because it's a very easy test. You just take the limit of an. If you're lucky, that limit is not 0 or that limit does not exist. Then the test works. You would say that, okay, this series is divergent. But if you're unlucky and that limit is equal to 0, then the test for divergence would be inconclusive. And in that case, you would have to use other tests. And those other tests are called the integral test and the comparison test, which we're going to talk about now. Are we good? Okay, so now what is the integral test? The integral test says that suppose f is a continuous positive and decreasing function. It needs to have all of these. F needs to be a continuous positive and decreasing function from 1 to infinity. And an, which is the general term of the sequence, is equal fn. So for example, think of f of x is equal 1 over x. If I graph this function, I'm going to show you the graph. One over x. So from here on, that is 1. This function passes through the point 1, 1. And then after 1, you can see that this function is continuous. There is no break. It is decreasing and it is positive. It has all those properties. Continuous, decreasing, and positive. And if I define an to be 1 over n, then f of n would be equal 1 over n, which is the same as an. That is, for a sequence like this, 1 over n, n from 1 to infinity, I can use this function and the integral test. By the way, this is called the harmonic series. It's a very important one. So suppose f is a continuous, positive, and decreasing function from 1 to infinity. If f of n is equal an for all the n greater than or equal to 1, then this series here and this improper integral, either both of them converge or both of them diverge. That is, if the improper integral diverges, then so does the series. If the improper integral converges, then so does the series. So in order to see whether this series here converges or diverges, I will have to calculate this improper integral and see whether that one converges or diverges. By the integral test, if this improper integral converges, then the series also is convergent. If this one diverges, then this one also is divergent. And you know how we calculate this? We calculate this in terms of a limit. We say this is limit as b approaches infinity of integral from 1 to b of 1 over x dx, which is going to be limit b to infinity of ln of x from 1 to b. That's going to be limit of ln of b minus ln of 1 as b approaches infinity. So we know that this part is 0, so it's limit of ln of b as b approaches infinity. And what happens to ln function as the argument to the function goes to infinity? That's going to be equal infinity. So this improper integral is divergent. It does not approach a finite number. Then by the integral test, we know that this series, which is called the harmonic series, is also divergent. Now let's take a look at another example. Imagine I ask you this. We have sigma 1 over n squared, n from 1 to infinity. And I'm asking you, let's say this is S, I'm asking you whether this series is convergent or divergent. Yes? You would probably first do, and this is actually something that you have to do. Let's go for the easiest test possible, the test for divergence. What happens if I take the limit of 1 over n squared as n approaches infinity? Unfortunately, that is 0. Okay. So that means this test is inconclusive. I cannot go anywhere with this test. So this test is out. What about the integral test? Can I define a function that is increasing, that is decreasing, positive, and continuous, so that f of n is equal an? Yes, it's very easy. I just need to define 1 over x as 1 over x squared. Because if I do so, then f of n will be 1 over n squared. And this function is decreasing, it is continuous, and it is positive after 1. So it has all these conditions. Okay, then I just need to calculate this integral from 1 to infinity of 1 over x squared dx and see whether this integral is convergent or divergent. If this is convergent, then so is the series. If this is divergent, then so is the series. That's the integral test. So this is going to be limit b approaches infinity, integral from 1 to b of 1 over x squared dx. That's going to be limit b to infinity of, okay, the antiderivative of 1 over x squared is negative 1 over x. It's negative 1 over x from 1 to b. That's going to be limit of b approaches infinity of negative 1 over b minus 1 over 1. And you can see that as b approaches infinity, this part is going to approach 0. And then I have 1 minus 1. That's 1. That's equal 1. That means the improper integral that I created is convergent, then so is this one. Notice that it doesn't mean that s equal 1. It does not mean that. This test does not give you the value of the series, unlike the previous two types of series that we looked at. When you looked at the telescoping series, we were able to evaluate s. When we looked at the geometric series, we were able to calculate the value of the series. But with this test, you can just tell whether it's convergent or divergent. You cannot evaluate it. So that's the only thing you can tell. You can say that since the improper integral is convergent, then so is the series. Are we good? Any questions? So here, the example 1 over n squared, we looked at that one together. And then we have the example for 1 over n. We also looked at that one together. Here we have another example where you can use the integral test. So imagine I give you this. Sigma ln of n over n from 2 to infinity. And I ask you to determine whether this is convergent or divergent. The first thing you're going to do is use the test for divergence, because you may be lucky and this will work as n approaches infinity. Okay, this limit is the same as having the limit of ln of x over x as x approaches infinity. So I can use L'Hopital's rule because this is infinity over infinity. So I get limit of 1 over x over 1 as x approaches infinity, and this is clearly 0. Okay, that's unlucky. That means the test for convergence, the test for divergence is inconclusive. So the test for divergence is inconclusive. If this was not 0, or if this limit did not exist, then we didn't have to do anything else. We would just say that the series is divergent. However, since this limit is equal to 0, this test is going to be inconclusive and we need another test. And the other test that we can use is the integral test. because we can define f of x to be ln of x over x, and in that case, f of n will be exactly ln of n over n, which is an. This part here. Make sense? So here you have the solution. You have to find the limit as of ln of x over x dx from 3 to infinity. So this starts at 2, n equal 2. So you can do it from 2 to infinity as well. There is no difference between these two. You can start from 2, from 3, or you can start from any finite number. It really doesn't matter what number you put here. Yes, as long as it's greater than 2. So here you have 3. I don't know whether there is any explanation for that choice here. It says that here an is ln of n over n, and so we consider the function ln of x over x. Observe that this function is continuous, is positive, and it is also decreasing from 2 to infinity. In order to check this, you need to look at the first derivative. When you take the first derivative of this function, you can see that the first derivative is going to be negative when x is greater than e. So yeah, that's the reasoning behind this. This would be negative if x is greater than e, because the moment x is e, ln of e is going to be 1, and when x is greater than e, ln of e is going, ln of that number is going to be greater than 1. So this numerator here will be negative. That means right after e, this is going to be a decreasing function. I can actually try to graph it. Ln of x over x. So exactly at e, you're going to have a local maximum and an absolute maximum for this function. Right after that, it's going to be decreasing. So from here on, it's decreasing, positive, and continuous. It has all the conditions of the integral test. And in order to see that, if you don't have a graphing tool, you have to take the derivative. You take the derivative of the function, and you ask yourself, okay, where is this derivative negative? Because negative derivative means decreasing function. And if you solve this, the numerator equals 0, you can see that x is, when x is e, the numerator is 0. If x is greater than e, the numerator is going to be negative. That means the function is going to be decreasing. So that's why the first number after e has been chosen, number 3, because e is 2.7. And when you calculate this integral here, you can see that this is going to be infinity, this indefinite integral, improper integral. And this is an easy one to do because you just need to do a substitution. You take ln of x to be u, dx is going to be 1 over x dx. And since this improper integral is divergent, then you conclude that the series also is divergent. Are we good? Any questions? Okay, so I think I also covered the P series today, and then let the test for comparison to be for next class. Another type of series that are very easy to tell whether they are convergent or divergent are series that have this form, sigma 1 over n to the power of p, as n goes from 1 to infinity. This type of series are called P series, and I have already shown you two, sigma 1 over n and sigma 1 over n squared, n from 1 to infinity, n from 1 to infinity. So for this one here, p is 1. and we looked at this one, it's the harmonic series, we showed it to be divergent. So this is a divergent P series. And in this other one, P would be 2. And we also looked at this one using the integral test. We showed that this is convergent. But any series that has this form, for example, if I have 1 over root n from 1 to infinity, that would also be a P series, because this is like having 1 over n to the power of 1 over 2, n from 1 to infinity. Here, P is 1 over 2. Any series that has this form is called a P series, and just by looking at that, you can tell whether the P series is convergent or divergent. And that's the easy rule. If P is greater than 1, the series is convergent. And if P is less than or equal to 1, then the series is divergent. So that's the theorem.
Can you repeat that? What did you say?
Yeah, you have it over here.
Oh, okay. Okay.
The P series, which has this form. I mean, what really matters for you guys is to practice enough so that by looking at the series, you can tell whether it's a telescoping one, or is a geometric one, or is a P series. Yeah, and the P series, they look like this. So I gave you 3 examples here. Then just by looking at that and telling what P is, you can tell whether it's convergent or divergent. The moment P is greater than 1, it's convergent. So for example, this one here is convergent. But if P is 1 or less than 1, like in this one, P is 1, or in this one, P is 1 over 2, it will be divergent. I'm not going to go to talk about the proof, just let's look at these examples together. Example 5.
Sir, can you
Yes?
go back to the theorem for 5 seconds?
Sure.
Thank you.
So for example, this one here, sigma 1 over n squared, and from 1 to infinity, we have already shown that this is convergent using the integral test, but you don't need the integral test for this one. Why? Because it's a P series and P is 2. 2 is greater than 1, so convergent. That's it. Or when you look at this one, sigma 1 over root n, and from 1 to infinity, that's sigma n from 1 to infinity 1 over n to the power of 1 over 2. So P is equal 1 over 2. Since it's a P series where P is less than 1, then it is divergent. That's it. So in a test, you would have to just do this. You find P, and you state that you recognize this to be a P series where P is less than 1, and so it is divergent. Another example, part C, sigma n from 1 to infinity n to the power of negative 1.001. This is sigma n from 1 to infinity of 1 over n to the power of 1.001. You can see that this is a P series now because it follows the form 1 over n to the power of P, where P is 1.001. So since this is a P series and P is greater than 1, it will be convergent. So we rewrite this in this form, and then we recognize that this is a P series. And since P is greater than 1, then we conclude that this series is convergent. And the way to prove this theorem is also very easy. You have the proof here. It's simply using the integral test. Because you can just, if you have a P series 1 over n to the power of P, you can define a function f of x to be 1 over x to the power of P. And then you can look at the improper integral 1 over x to the power of P from 1 to infinity dx. And you will see that this improper integral is convergent if P is greater than 1. And it will be divergent if P is less than or equal to 1. So for that reason, the P series would be convergent if P is greater than 1, and it will be divergent if P is less than or equal to 1. So I'm going to end the lecture now. Let's say this is part 1 of the lecture. I will cover the rest of it next class, or maybe after the test. For now, I'm going to open this set 11.4, so that you can start working on it. There's only this comparison test, one theorem, which I will cover. I think I'm going to cover that next class. Okay, so